Let me welcome everybody to my talk on trends in industrial turbulence modeling. My name is Florian Menter. I'm speaking here from sunny Bavaria, as you can see, in Germany. And the talk is not really about a very specific research item we are working on, but more an overview of what we have been doing and where we have been concentrating over the last few years. And the emphasis on RANS modeling. Of course, we do a lot of work in scale resolving LES and hybrid runs LES modeling, but the main thrust of work in industrial simulation is still RANS. So we still have a strong focus on RANS modeling, and I just try to give you an idea of what our current thinking is on this topic here. Now, the main workhorse in CFD is two equation models. And two equation models, in its simplest form, they have 5 coefficients, which are calibrated to match physics of fairly simple cases like flat plate flows and mixing layers and so forth. And these coefficients are then exposed in the graphical user interface to the user, but in reality, we don't want people to change it because these coefficients are all interrelated. And if you change one of these coefficients, there's a big danger that you really destroy the calibration of the model. So there is very little to none flexibility in these classical two equation models. And the question is, can we, in the long run, capture these very complex flows we have to deal with these somewhat simplistic models and models which have no flexibility in themselves? And in order to address that issue, we started out defining a new family of models, which we call generalized K-omega or GEKO models. Now, formally, the model is a standard K-omega model, as you see here, but the model has some additional functions here, F1, F2, and F3. And these functions contain coefficients, and these coefficients are free to be changed by the user without destroying the basic calibration of the model. So we try to put flexibility into the model and expose a number of coefficients which the user can change in a certain range, and it causes certain effects which are predictable, and then they can be used to optimize the model for specific applications there. The coefficients of main interest are CSEP, which controls the separation characteristics. So if we increase it, we get more separation, and if we decrease it, we get less. We have a mixing coefficient, which affects the mixing in free shear flows, for example, mixing layers or combustion chambers or other free shear flows. We have a coefficient which is a near wall coefficient, which changes, for example, details of heat transfer in non-equilibrium flows. And then we have one where we can control jet spreading rates. And there is others which are more general in use, corner corrections and curvature corrections. Now, all these coefficients are field variables. So they are not only constants, but they can also be accessed via user-defined functions and later on expressions, and you can change them in the entire domain according to whatever is the best value for the application. Now, the first question is, why do we use the K-omega model? And I always have liked the K-omega model because it's very robust. It doesn't need a lot of terms to be integrated through the viscous sublayer. And it doesn't have any pseudo transition, so it transitions very early unless we use a transition model. And here you see a backward-facing step flow, and you see the wall shear stress and the heat transfer coefficient from different types of models. So we have here a standard K-epsilon model with a low Reynolds number treatment, which gives huge heat transfer rates. We have a K-epsilon model with a 2-layer model near the wall, which is the orange curve, which is much too low, about almost 50% lower than the experiments. We have a V2F model, which is the red curve, and then the K-omega type models. And they are much closer to the experimental data than any other of the two equation models. So I think they form a very robust starting point for simulations. Now, of course, if you have these 4 major coefficients, you have to be careful to be able to tune them. And if they would be active everywhere at the same time, it would be very hard to balance one against the other. So we have divided them into groups, and the 2 CSEP and C near wall are active near the body, So they affect essentially the boundary layer. And the C-mix and C-jet, they're active in the blue area, and they affect the mixing layers and the free shear flows. So they can be tuned rather independently to a degree of one another. And this is all separated by a blending function, which is similar to what we have in the SST model, really. Now, here's the main idea behind the model. Of course, it's not a very spectacular picture, but it shows something which is important here, namely that we ran a flat plate and we change the two coefficients which are affecting the near wall behavior, the CSAP and its near wall coefficient. And you see we can change them rather dramatically, and we still maintain the wall shear stress and the log layer behavior. So we are not destroying the basic calibration of the model when we do that. Now, here we did a test where we ran a flat plate and we changed the main CSAP coefficient here from 1 to 175, about 40% down the plate. This is here, and you can see there's a fairly smooth variation of CF here, so you can hardly see that place where it changes. And if we look at the eddy viscosity ratio, we can see that this is the GEKO with CSAP1, which is similar to a K-epsilon model. This is with the default 175, which is more like an SST model, gives somewhat lower eddy viscosities. And then if we change here in the middle of the flow, we get a smooth variation. The upstream is more like the GEKO1, and the downstream is more like the GEKO 175. So we can have zonal formulation of this model without having any kinks in the solution themselves. Here you can see the behavior of the model for jet flows, and everybody familiar with two-equation model knows that jet flows are not easy to compute. Typically, we get an overprediction of spreading rates for the round jet. So if we use, for example, a K-epsilon-like setting here, the black curve, we get much too high spreading rates, which, for example, for heat transfer problems, if you have impinging jets, is very undesirable. And if you change the CSAP to the default of 0.9, we can have, for both cases, very good spreading rates in agreement with the experimental data. So this is a kind of a side effect of this model tuning. The main effect, and what most people use these coefficients for, is separation control. So here you have an airfoil at different angles of attack. And if you look at the 12-degree angle of attack at the trailing edge region of the airfoil, we can get a large variation of solutions by changing the GEKO CSAP coefficient. So if we have 1, we get something like a K-epsilon behavior. If we get 175, we're pretty close to data. It's like an SST model. But we also can force it to over-separate with CSAP being in the range of larger than 2. We can get more massive separation there. So if we have a certain application and you need to tune the model, this is the coefficient to tune the separation characteristics. And it works for all sorts of flows. Here you can see a transonic flow, transonic hump flow of Batchalo and Johnson at NASA Ames. So there's this flow with 0.875 Mach number, goes supersonic, has a shock wave here, a boundary layer interaction separation region here. And the separation determines the shock location. So if we go again with a conservative setting, like GEKO 1, which is more like a K-epsilon model, we get a very backward shock location, and we can then tune the shock location by changing CSAP. Now, the blue curve is the default. So I want to mention that, of course, we have very strong defaults, which are similar to SST. So you don't have to tune the model for every flow you're running, but you can do that if you feel a need for that and you have good experimental data justifying these modifications. Here's another test case where you have a diffuser flow, and the diffuser has a small separation bubble here. So you have an axisymmetric diffuser with a wall opening up and causing a drop in the wall shear stress here. And we have these two coefficients, CSAP and C near wall, both affect the near wall behavior, but the CSAP changes really the separation characteristics, where the C near wall only affects the kind of the very close region to the wall in the separation area. And you can see here the C-sep changes the pressure distribution. I don't know whether I can get rid of this one here. And you can get the pressure plateau from the separation, whereas you cannot do that with the near wall coefficient, which only changes the very near wall behavior. You can see that better here in these velocity profiles. The C-sep does what it does on the airfoil. It goes from an attached flow to an over-separated flow if we increase the coefficient here, whereas the near wall coefficient only really changes the characteristic of the model near very close to the wall, and that can have positive effects if we dealing with, for example, with heat transfer in non-equilibrium conditions, because then this coefficient can be used to control the heat transfer near wall behavior. You can see that here again for the backward-facing step. This is a backward-facing step which has a heat transfer region here. So there is constant heating at this wall, and we predict that flow then with different settings of the near wall coefficient, first for C-sep1 and then for C-sep2. And you can see with the near wall coefficient, we hardly change the separation reattachment region, but we change the heat transfer Stanton number here in the reattachment area close to reattachment of the flow quite dramatically. So we can change it by maybe something like 50–60% here, and the same for C-sep2. So it's a very independent. It's a parameter which is fairly independent of the C-sep setting here. Again, the default is the green curve in this picture here, this 0.5 value, and it of course has been tuned to match generic flows as well and as good as possible. So again, hopefully in most cases you wouldn't need to change that coefficient, but if there is a need and you have good experimental data, you can actually adjust the heat transfer in these non-equilibrium flows by using that coefficient there. Now here's another interesting problem that we often face. It's a flow behind bluff bodies. And of course, in reality, what you have a vortex shedding here. You have a turbulent von Karman vortex street here, which at least in its initial stage is an unsteady phenomenon. It's not really a turbulent mixing, but it's an unsteady mixing from the flow flip-flopping from one side to the other. And in reality, you should do that with an unsteady simulation. It's not something really any turbulence model is tuned to capture. But there can be scenarios where engineers don't want to do unsteady simulations because it's too expensive. One example is Formula One cars. In Formula One, we have these bluff body areas, for example, behind this wheel, but they have very tight regulations on how much computing power they can use, and they have to balance the computing power they use against wind tunnel time. So they are very frugal in using computing power, and they do some scale resolving clearly, but then they like to match the scale resolving simulations with the GEKO model and tune the C-mixing coefficient so they get a much better agreement, for example, in this area behind the front wheel. And this is kind of a generic example here. If we run steady state for this triangular cylinder, we get a very large separation zone as we expect, and then we can increase the C-mixing coefficient in these free shear flows here, and then we can reduce the separation zone dramatically, even though we're just doing a steady state simulation. And you can see that here with the turbulent viscosity ratio, which is of the order of maybe 1,000 here, maybe 1,500, and then you can increase that, and it goes up all the way to several thousand ratio values here, and that causes this rather reduction in the separation bubble. And if you look at a line here in the symmetry plane behind the body, and you look at the velocity u, you can see that the default, of course, is far off the recovery of the model of the flow that we see in the DNS or in the experiment. And then if we increase the mixing coefficient, we can get a much better agreement. We don't capture all the details. The separation depth is underestimated if we do that. But in this case, it would be important to get the proper inflow to the back wheel, for example, and then it's much better to have that level here than to have this very low level of velocity, which would severely affect the downstream area. So this is something which is clearly somewhat outside the envelope of RANS modeling, but you can still force the model to capture at least the main effect of this mixing area there. Now, another topic we have continuously been working on for the last almost 20 years. Now it's exactly 20 years by now, is transition modeling. And some of you are familiar with our work. We have introduced a concept that is called local correlation-based transition models. And the idea is to have RANS models which inside the boundary layer can detect when is transition onset, and then when that happens, these models can trip the boundary layer. And this is what you see here is the intermittency. So if it's 0, it's laminar, and if it's green, it's 1. It's fully turbulent. And we used a fairly engineering type approach there. We started, the first model was published in 2002, so exactly 20 years ago now, in a few months. And then we published the gamma or theta model in different papers, which is the main model used in industrial use today. We reduced that model later on to one equation, gamma model, fully published, and then we used the gamma model where we eliminated the or theta equation. And recently we have even reduce that to an algebraic model. So we don't have to solve any transport equation anymore for the transition model. That is motivated by the observation that in these transition models, the source terms are very dominant, and the convection and diffusion terms are actually not playing such a major role in the balance. And so you can essentially live with a source term equilibrium formulation there. Now, the way these correlation-based models work is you build a ratio. In the numerator, you have the actual current state of the boundary layer at the place where you are, and that's represented by a Reynolds number based on the boundary layer thickness, and you divide that by a correlation which tells you when the boundary layer should transition. And if that ratio, so this green ratio is going up, this green value is going up as you go downstream in the boundary layer, whereas the correlation typically stays more or less constant. And eventually this ratio reaches 1, and then we trip the boundary layer. And it's tripped where we typically use the vorticity Reynolds number here, and that has a maximum in the center of the boundary layer. And if that maximum exceeds the correlation, like here, it goes across this line here, then we start to trip the boundary layer in the center. And that's exactly that point here. And then it takes a bit of time or running length to transition the boundary layer fully. And these correlations here, they essentially curve fit of experimental data. They depend on turbulence intensity and the pressure gradient inside the boundary layer. So if you have, for example, no pressure gradient lambda, and we have a low turbulence intensity, we have a transition at about 1200 RE theta, so fairly downstream. And if we increase the turbulence intensity, we would have it at about 200, so much further upstream. And we consider that a fairly convenient way of handling transition, because we don't model the transition, we just use what we know from the correlations. And there's, for example, here's bypass transition, here's natural transition. But the correlation, the model doesn't care about what physical phenomena it is. It just takes whatever correlation it gets and trips the boundary layer there. Now, the way this new model is formulated, it was published maybe 3 months ago at the ETMM conference in Greece. So there's a paper on that. We multiply the pK term in the turbulent kinetic energy by gamma. And the gamma is just an algebraic formulation of this onset function. And the onset function is, as I said, basically the vorticity Reynolds number by the correlation. And of course, then you need a correlation, which is given here, which is essentially 1 over TU with some sophistication. Then there is an effect of pressure gradient, which comes from this lambda term here. And then we have an additional provision for bubble transition. We know that in a laminar separation bubble, we have to kind of push the model a little bit harder to transition, otherwise the bubbles get too long. So essentially all recent RANS transition models have adopted this approach of having some kind of forcing term in the laminar bubble. And of course, there is coefficients which are accessible to the user and which can be changed and have a physical meaning, so you can control the process. Now, we did a lot of cases, and I just show a few of them here. These are flat plate boundary layers with different turbulence intensities. So here's the lowest turbulence intensity, and here's the highest. And we compare the new algebraic model, the green curve, with the gamma 1 equation model and the gamma RE theta. And by and large, here's with pressure gradients, a number of cases all the way down to separation. By and large, there is not a lot of give and take between these models. One is a little bit earlier, one is a little bit later, and we'll see how that balances out. But we could probably even calibrate them more closely. But sometimes it's better to have a bit of variation in calibration, that people can use different models if one of the models doesn't do exactly what they want, or you could use the coefficients again to tune them. So we have a fairly cheap way to handle transition, which of course also for heat transfer problems we found to be very important. For example, impinging jet flows typically are much better predicted if you use a transition model, because the stagnation area where the boundary layer starts off from the impingement point is typically laminar, and then there's a transition further downstream, and it's good to include the transitional model. An interesting combination then is if we use hybrid runs LES models, and we use what we call stress blended eddy simulation, which is a somewhat more sophisticated version of detached or delayed DES methods. And in these methods, the boundary layer in its classical usage, the boundary layer is captured in RANS mode. So the models try to capture then the separated flow in LES mode and the boundary layer in RANS mode. Of course, that means that if your RANS model doesn't predict your separation points correctly, all your unsteady simulation doesn't help you, because you don't get the benefit from it, because the RANS model dominates the flow. So we can use again GEKO to tune the separation behavior of the model. And you can see here a case which we got from our customer Fiat Chrysler Automotive, and they were interested in noise going through that side window. And here you see two simulations with the SBS model, one with GEKO CSEP1 and one with GEKO CSEP2. And what you see here, the separation behavior on the A pillar is very, very different. And this one is separating much stronger and has much more vortices there, which of course then affect the noise going through that window. And here you can see the side window and the measurement points where the pressure fluctuations were measured. And you can see then a comparison of the simulation with the SBS model and the experiments. And you see the biggest difference, of course, is in locations 8, 9, and 10, which is exactly the region where the A pillar vortex impinges on the window. And we can tune that by using certain settings for the GEKO model, particularly CSEP settings, which are optimized here. Okay, so that's an interesting option that we don't have to take whatever we get from the RANS model in a hybrid formulation, but we can also optimize that. Now, in order to further increase flexibility, let's look at a few things we can do with the GEKO coefficients beyond global changes. We had a workshop last year in 2020, I think it was, where in Oxford, where there was a comparison of dry-air fastback and dry-air estate. So these are two generic car models originally coming from the Technical University in Munich. And there's experimental data. And in this case, my colleagues, they used the design of experiment to define the optimal GEKO coefficients for these applications there. And they defined 3 different coefficients: one CSAP global, one CMix global, and then they used a zone around the wheels where they allowed CSAP to be different from the global value everywhere else, because the wheels are aerodynamically very different from the body. And so they felt that it was a sensible idea to tune the wheel area separately. So they had essentially 3 coefficients here, and they wanted to know what is the best value for these coefficients for these automotive simulations there. So the target value was drag and lift for both cars. They ran design of experiment about 20 simulations. That's about 6,000 CPU hours. So if you have 250 cores, that takes you about a day to run those. It's about the cost of a single scale resolving simulation there. And they determined then the optimal coefficients. And here you can see the comparison for the estate car. This is the wake with the standard coefficient, and this is the wake with the optimized coefficients. Note that the only parameter which was going into the optimization was the experimental drag prediction. And they used the same values for both cars. And you can see this is the default. The scale here is rather small scale here, so it's an exaggerating scale. And you can see that we can get a significant improvement for the fastback towards the experimental data, but even more though for the estate. And you would imagine that happens because it's less of an aerodynamic shape, and it has more wake influence, and the wake is, of course, with RANS typically overpredicted. So we get here a very close agreement with the experimental data using that optimization. And it's a fairly simple thing. And I personally think that when we talk about optimizing turbulence models, it will be exactly this type of optimization. It will be, I think in English you say horses for courses. So you're probably not very successful in getting much improved generalized turbulence models, which are much better for any application. But an engineer, most of the time, is dealing with the same type of problem, like, for example, car design. And then they can tune a model to match certain experimental values, and then they use that tuned model for making changes to that model. And then they start out with a much more realistic initial condition for their optimization process. So I think that's probably what we're going to see there in the future more and more. Of course, the next step, and what a lot of people are working on these days, is machine learning. And you don't want to maybe do that optimization by hand, but want to have a machine or artificial intelligence do that for you. And the simplest example is you have an airfoil, you know the lift coefficient from the experiment, and you want to change CSAP in ways that you get the optimal lift representation there. And in this case, it's not about changing CSAP globally, but it's about changing CSAP in each cell of your computational domain. So it's a field variable, and what is the most optimal distribution of CSAP in the field to get the experimental value. And in order to answer that question, you need to know how the error function or the objective function here, which is the difference between the predicted lift and the experimental lift, how is that affected if I change the CSAP coefficient in one single cell? And in order to do that, you need to create a derivative, a DE divided by d CSEP and delta CSEP, and that you can do chain rule, dE divided by the lift. It then focuses in on the surface faces on the pressure, but then you need to know how these lift cells change with CSEP, and that's a very, very complex question. If I change CSEP somewhere in the free stream, how does it affect the lift coefficient on the body? And for that, you need an adjoint solver. And my colleagues have implemented an adjoint solver for the GEKO model in Fluent. And the solver can predict exactly that gradient. And then, of course, you can use a gradient method or conjugate gradient method and go down the slope and find the minimum. And then you get a CSEP distribution for that application, for that wing or airfoil at those conditions. And that looks something like that. Here you can see the solver convergence and the adjoint solver convergence and the flow field. It's kind of this here with a shock wave. And you see the
Florian,
CSEP.
We have another 10 minutes.
Sure. Yeah.
If you can wind up maybe in 5-6 minutes, we can have a couple of questions.
Sure. Yes. Okay, I'm going to be able to do that. So you see here the CSEP coefficient goes down exactly in this area where you would expect it in the separation zone, and a smaller CSEP gives you less lift. So it's a negative correlation there. But then the question is, if you have this CSEP coefficient distribution, it's only valid for a single case, and that's not a good idea. What you want to do then, you want to relate that CSEP distribution to field variables in these cells and see whether there's a correlation. For example, CSEP going down, is that correlated to maybe phi1 going up, and phi1 being a non-dimensional strain rate divided by the omega from the K omega model, or mu T over nu. So you can train your neural network with some input quantities, which we have some predefined ones. You can also use additional ones. And then you can train that neural network to match the CSEP coefficient. And once you have done that, you have to, of course, converge that. And then you get a field for this coefficient. In this case, we had a coefficient in the omega equation. And that is then trained. And you can see that with different coefficients, we can get a pretty good representation of the flow. In this case here, when the flow goes beyond maximum lift, it stalls actually. So it becomes 3D, and we have only 2D simulation, so we cannot capture that. But otherwise, the agreement is quite well. And so we can find a good correlation between CSEP and local values using the neural network. However, this is, of course, a fairly trivial exercise because we can achieve the same behavior for many airfoils by just tuning a global value for the GEKO coefficient. So there's still not clear how much machine learning we will need, because GEKO in itself has so much flexibility already that a lot of things can be done without machine learning, which is, I think, good for the user because it's much more transparent. And we will see how far we can push that, and at which point we have to move into the more complex machine learning processes. Finally, there is one case which some of my colleagues have done for this periodic hill, and we have a DDS solution there. And we start out, we try to match the velocity distribution, the mean velocity distribution in this domain. We start out with an error of 5, and we can reduce it to about 0.7, and then train the neural network. And you can see here that the DNS data, the standard GEKO, all the RANS models which separate properly have this overprediction of separation zone. We know that also as Spalatamara, so SST. And with the machine learning, we can reduce the size. It's not perfect, but it's much closer to the data. Now, of course, if you do that, we don't know whether with this calibration, if you use that neural network now for other applications, whether it would be beneficial or whether it would be negative. And that's always the problem, is that how generic is that? So you would really, instead of doing just this one case and optimizing it, you would also have to include in the training data a lot of the basic flows, for example, a mixing layer or backstep, which you don't want to change because it's already pretty good. And then the question is, can you still optimize that? And that's a question we are kind of looking into in these days, and see how generic this all is. So in summary, I don't go to all these points. I have said that all in detail. I think GEKO is a fairly the most flexible model out there. I'm certain at current point, and can be augmented by design of experiment or machine learning processes to optimize it. And for those who are interested a bit more deeply into the details, we have best practice for the GEKO model. There's also a very new version of, not a new version, a new report, best practice on RANS modeling, and we had an older one on scale resolving. And these are typically freely available. So if you're interested, you can get them.
Thank you.
All right, thank you.
Florian. Yeah. So yeah, we have another 5 minutes probably. So are there any questions from the audience? Otherwise, I have maybe a couple of them.
So I will first announce. Maybe if you want, you can ask those questions then. Then we can just have some time to get any questions.
Okay. So yeah, Florian, while some questions come in the chat box, one question I have is that did you explore this GEKO models in rotostatic cavities? I'm particularly from turbomasonry background, so did you try?
No, we have our colleagues in the turbo machinery group are starting to explore what they can do with these models. And of course, we look currently at single blade flows, and of course, there you typically, if you depends a bit on the blade. If you have compressors, the finding is that you want to back off a little bit on the CSEP coefficient to get more deeply into the stall region. But we don't have a paper or anything on that at current point.
Dr. Menter, I have a question from my side. This is Arvind Pattamata here. You had presented a very nice overview of the GEKO model with about 6 of these parameters, which are floating parameters, and that can be optimized for different kinds of flows like separation and jet flows and all that. But how do the user really know the values that he has to choose for more complex flows? For example, we have flows where we have the combustion liner cooling, where we have a combination of jet and boundary layer, like a wall jet and mixing layer kind of flows. So for that kind of flows, how do the user really know the combination of these parameters, the best parameters that he can choose for the simulations?
Well, I mean, you cannot theoretically determine that, and there's no fixed recipe. I think the best starting point is to take this report I have just shown, the best practice on GEKO, to understand the mechanics of the model and to know what these different coefficients are doing and which area they are really active. And then you look at your flow, and often you can see, well, I don't have enough mixing here. Maybe I change the mixing coefficient. So my separation zone is too long, so I change the mixing, increase it, and I get a smaller separation. And you initially you probably just play around with that by hand. And but if you don't want to do that, of course, then you can go and through these processes I have described, for example, a design of experiment, where you just define the number of coefficients you think are necessary for your flow to tune, and then try by a more automated way to optimize these coefficients there. Or, as I said, eventually you can go to a machine learning process. But of course, it depends strongly on the flow that you're looking at, which coefficients you need to change. If you have an aerodynamic, it's mostly CSEP. If you have a mixing flow, it's mostly the mixing. If you have a heat transfer, it's probably mostly near wall and the mixing coefficient. So it's really a case-dependent question.
Thank you.
So do you have any suggestion for the users in absence of test data? So how somebody can come up with a combination, probably suppose.
Yes. Sorry. There's a very strong recommendation. If you have no test data, use the defaults. Because if you have no guidance from either experiment or DNS or anything else, how would you want to change the coefficients? You cannot change the coefficients, and the default values are the best values we could find for an overall coverage of flows. So if you have no data, there's nothing you can do really.
Okay, thank you so much, Florian, for your wonderful talk on the GEKO model. So I think with that, we'll close this session here.